Lecture 14 covers Section 5.3.3. At the end of today's lecture, you should be able to identify and understand the conditions necessary for static structures to be in equilibrium in 3 dimensions. For us to have equilibrium in 3 dimensions, the following system of equations must be satisfied, i.e. they are necessary. Our total reactionary force on our system, which is the sum of the forces in the x direction, plus the sum of the forces in the y direction, plus the sum of the forces in the z direction, has to be equal to 0. This means that each of our forces, or the summation thereof in our principal directions, identically have to be equal to 0. Additionally, the resulting couple on our system, which is the sum of the moments in the x direction, plus the sum of the moments in the y direction, plus the sum of the moments in the z direction, also has to be equal to 0. The reactions from the supports that we apply to our system must be sufficient to constrain our body, i.e. to prevent motion. Let's look at an example where we have a uniform pipe cover that has a radius of 240 millimeters, and the pipe cover has a mass of 30.0 kilograms. Now, it is held in a horizontal position by cable CD. We're going to assume that the bearing at B does not exert any axial thrust, that is, it is not a thrust bearing, but the bearing at A is. We want to determine the tension in the cable as well as the reactionary forces existing at A and B. For us to begin, we will draw a free body diagram of the system. We see at point B we have a reactionary force in the y direction and the x direction. There is no reactionary force in the z direction, for the bearing at B is not a thrust bearing. At A we have reactionary forces in the x, y, and z directions. Lastly, we have tension existing in our cable that goes from point D to C. Now we have the weight of the lid applied at the center of the lid. That is, our applied force is W. If we look at our system, we have 6 reactionary forces: RAX, RAY, RAZ, RBX, RBY, and the tension in our cable. Now, in terms of applied force, what is our weight? Well, our weight is going to have a magnitude and a direction. Our weight is equal to our mass times the gravitational acceleration, and it is going to exist in the minus y direction. So you have 30 kilograms times 9.81 meters per second squared existing in the minus j hat direction. Or we'd have minus 294 newtons in the j hat direction. Now, in terms of our applied forces, we need a unit vector describing our tensile force, i.e. the unit vector describing the line DC. And to do such, we can say E hat DC is equal to the vector DC, which is minus 480 millimeters in the x direction, 240 millimeters in the y direction, and minus 160 millimeters in the z direction per the magnitude of our vector, which is the square root of the sum of 480 millimeters squared plus 240 millimeters squared plus 160 millimeters squared. Or E hat DC would be equal to minus 0.859, 0.429, and minus 0.286. For us to determine the x, y, and z components of the tension in our cable, we can recall that our tension vector is equal to magnitude T times the unit vector describing it, E hat DC. So we can say the tension in our cable is minus 0.859 T, 0.429 T, and minus 0.286 T, where T is an unknown variable. We will construct an equilibrium equation for our forces. To begin, we'll say the summation of our forces has to be equal to 0. That is, in our x direction, the summation of forces existing within our x direction would be RAX plus RBX minus 0.859 T. Then we can look at the summation of forces in our y direction. We'd have RAY plus RBY plus 0.429 T minus 294. And lastly, in the z direction, we'd have RAZ minus 0.286 T. We can decompose our previous expression into our principal directions. That is, we can say the summation of our forces in our x direction is equal to RAX plus RBX minus 0.859 T. And this has to be equal to 0. The summation of forces in our y direction is equal to RAY plus RBY plus 0.429 T minus 294. And this is equal to 0. Lastly, the summation of forces in our z direction is equal to RAZ minus 0.286 T. And this is equal to 0. Currently, we have 3 equations and 6 unknowns. Thus, we have to look at our moment equations. The first equation we can apply is our moment of force about point B due to the forces acting at point A. That is, we can say our moment of force about point B due to the forces at A is equal to R1 cross FA, where R1 is our position vector going from B to A, which is described as 0, 0 to R. And our force existing at A is simply RAX, RAY, RAZ. And this is equal to taking the determinant of I hat, J hat, K hat, 0, 0, 2R, RAX, RAY, RAZ, which gives us the quantity 0 times RAZ minus 2R times RAY existing in the I hat direction, minus the quantity 0 times RAZ minus 2R times RAX existing in the J hat direction, plus the quantity 0 times RAY minus 0 times RAX existing in the K hat direction. Next, we can take our moment of force about point B due to our forces existing at point D, i.e. the tension in the cable. We can say our moment of force about point B due to our tension is equal to R2 cross T, where R2 is our position vector going from B to D, which is given as 2R, 0R. And we cross this with the tension in our cable, minus 0.859T, 0.429T, and minus 0.286T. This is equal to the determinant of I hat, J hat, K hat, 2R, 0R, minus 0.859T, 0.429T, minus 0.286T. And this gives us the quantity 0 times minus 0.286T, minus R times 0.429T, existing in the I hat direction, minus 2R times minus 0.286T, minus R times minus 0.859T, existing in the J hat direction, plus the quantity 2R times 0.429T, minus 0 times minus 0.859T, existing in the K hat direction. Lastly, we can take our moment of force about point B due to the weight of the lid. That is, we can say our moment of force about B due to W is equal to R3 cross W, where R3 is our position vector going from B to the point of application of our weight, which is given as R, 0, R. And we cross this with our weight, which is given as 0, 0, minus 294. So we'd have the determinant of I hat, J hat, K hat, R, 0, R, 0, 0, minus 294, which gives us the quantity 0 times minus 294 minus R times 0, existing in I hat direction, minus R times minus 294, minus R times 0 in the J hat direction, plus R times 0 minus 0 in their K hat direction. The only way for us to have equilibrium is if the sum of the forces and the sum of the moments in all our principal directions are equal to 0, which means we can take the sum of the moments about point B, which is equal to R1 cross FA plus R2 cross T plus R3 cross W. And this gives us minus 2 RAY minus 0.429T plus 294 times R, existing in the I hat direction, plus 2 RAX minus 0.286T times R in the J hat direction, plus 0.859T minus 294 times R in the K hat direction. And this has to sum to 0. Deconstructing our moment equation in the K hat direction, we see we have 0.859T minus 294 times R has to be equal to 0. Or we can say 0.859T is equal to 294, or the tension in our cable is 342 newtons. Looking at the J hat direction, we see we'd have 2 RAX minus 0.286T, quantity times R being equal to 0, or we can say 2 RAX is equal to 0.286T, and we can solve for RAX being 48.9 newtons. Lastly, in the I hat direction, we'd have minus 2 RAY minus 0.429T plus 294, quantity times R being equal to 0. Or we can say 2 RAY is equal to 294 minus 0.429T. Solving for RAY, we have 73.5 newtons. Lastly, we can substitute these values back into our force balance equation, noting that our principal components must be equal to 0. That is, we can say the summation of forces in the x direction has to be equal to 0. We have RAX plus RBX minus 0.859T is equal to 0. Given that we solved for RAX previously, as well as our tension, we find RBX to be equal to 245 newtons. For the summation of forces in our y direction, we'd have RAY plus RBY plus 0.429T minus 294 is equal to 0. Since we have RAY and T, we can solve for RBY being equal to 74 newtons. Lastly, the summation of forces in the z direction states RAZ minus 0.286T is equal to 0, or RAZ is equal to 97.8 newtons.